we'll go ahead and begin for tonight. So hello and welcome everybody. I'm Regina Jorgensen. I'm the Director of Astronomy here at the Maria Mitchell Association. And I'd like to welcome you tonight to what will be the last of our Winter Science Speaker Series talks. Tonight, before we begin, I'd actually just like to make a note. As you can see on the screen, we highly encourage you to ask questions if you have any. Please use the Q&A function, which is a button that you should be able to find if you move your cursor around, usually down at the bottom of the screen, and you can type your questions in there. I'll be monitoring the questions, and we'll likely just hold and take them all at the end. So but feel free to stick them in as they occur to you, and then we'll sort of address the questions in order that they came in. And I can say one other note, although this is the last of our Winter Science Speaker Series, we will be running a Summer Science Speaker Series that will be starting at some point in June. So look out for our notices on that once we start to advertise the dates of that. So tonight it is my really great pleasure to introduce our speaker, Rachel Bowyer. And Rachel is currently a third-year graduate student in a PhD program at the University of Colorado, Boulder. And I first met Rachel when she came to the Maria Mitchell Observatory as one of our National Science Foundation REU, or Research Experience for Undergraduates, internship. And that was in the summer of 2017, which now seems like a long time ago. While she was here, she actually worked on a project not dissimilar from what she's been working on recently. And this project was to study dark matter in galaxy clusters using weak gravitational lensing. And Rachel is one of the few, if not maybe the only, Maria Mitchell intern in recent years, at least, who actually contributed to a publication that came out during her summer here. Lots of our students end up publishing papers or being on papers, but it often takes some time to get the paper out. So it usually happens in the next year or two after their experience is over. So that was one distinction Rachel had of her time here. In 2018, she earned her bachelor's degree in astrophysics from Rice University and went on to start her graduate studies at the University of Colorado, Boulder. And in 2020, Rachel received an honorable mention in the very prestigious and competitive National Science Foundation Graduate Research Fellowship Award competition, which is sort of the kind of biggest, highest honor you can get as a STEM graduate student. And actually earlier this year, Rachel won the prestigious Chambliss Astronomy Achievement Award in the graduate division for her presentation of her work at the winter virtual meeting of the American Astronomical Society, which happened in January. And she was one of 6 awardees out of 96 entrants into the competition. So this was quite a special achievement as well. And I was actually lucky enough to be able to attend her comprehensive exam, which happened last fall, which she of course passed with flying colors and earned her master's degree and advanced to candidacy for her PhD. And I was so impressed with the way that she gave her presentation and discussed her research, which is really, it's not the easiest research to talk about, especially to non-experts. And she had such a fantastic way of describing the things that she was doing to people who had no experience in the field. I immediately thought of her when we were putting together this speaker series, and I knew that she would be a fantastic person to give one of our talks. In addition to all of her tremendous successes in her research career, Rachel has been actively involved in revamping the introductory astronomy course for non-majors at her university. And in order to do that, to make it more accessible to a range of people with different abilities. She's written articles about this work and was actually invited to present on her work at the Inclusive Astronomy 2 meeting, which happened back in 2019. Furthermore, she was also recognized by CU Boulder by the Center for Teaching and Learning with a Silver Award as an outstanding teacher and leader among graduate students. So we're very lucky to have her here with us tonight. And I'll just add one other personal story. Obviously her research accomplishments are great, and her interests and talents span a much wider range than just astronomy. And I'll just tell one story about her time here as an intern that I remember one night during an open night at the observatory. I noticed that the old Clark refracting telescope, which is over 100 years old, seemed to be making a louder noise than it normally does as it tracks across the sky. And I mentioned it to several of the interns who were standing there, and we kind of ho-hummed about it, and then it was late, so we just decided to go home, and I figured I'd come back later and in the daytime and sort of diagnose the problem. And before I even got around to doing that, I'm sure it slipped my mind or I got busy with other things, Rachel actually came to me and said, oh, I diagnosed the problem. I went and looked. It turned out in a little gearbox, there was a lot of material that shouldn't be there. It might have been a contribution from a mouse or something like that. And she had actually cleaned it out, fixed the whole thing, and got it running smoothly again. So really without any prompting, sort of repaired and got back into operation our historic Clark telescope, which of course we were very thankful for. So anyways, it is, as I said, my great pleasure to welcome Rachel here tonight. I'm very much looking forward to this talk. And like I said, if you have any questions, please put them in the Q&A and we will take them at the end. And with that, I'd just like to say thank you so much, Rachel, for taking the time to be here, and welcome, and I'll pass it over to you.
Great, thanks. That was an awesome introduction. She was like, "What? How should I introduce you?" And I was like, "Oh, just tell them I'm a grad student." But yeah, thanks so much for that, Regina. Yeah, let's get started here. Let me share my screen. Okay, I think it's working now. Okay, so today we're going to be talking about hidden patterns in galaxy motions and what they can tell us about the universe. And that's kind of going to get us into this realm of cosmology. So I'll tell you what that's all about and how we can use these galaxy motions to really tell us about our universe and what's going on today. This field is one that I've been working in for approximately 3 years while I've been in grad school at CU Boulder. And I should mention that while I'm going to include a lot of really general information about cosmology and it'll be really beginner friendly, the specific area of study, the galaxy motions area, is actually pretty new and pretty niche. So you probably won't hear too much about it in other contexts unless you kind of read specifically the science journals. So let's get started. Okay, so this is kind of our talk overview and outline. First, we'll go over the cosmology background, kind of what are the things you need to know about cosmology to understand the context of what we're going to be talking about, and how do we kind of study and quantify the universe. Then we'll move on to galaxy motions, and I'll talk about what they are, how we can measure them, and what these motions can actually tell us about the universe. Specifically, we'll go into the two most exciting areas, which are kind of the formation of structure as we know it today, and also gravitational waves. And then after that, we'll go into kind of the future directions of this field and what we can kind of do with galaxy motions going forward. Okay, so first, let's talk about cosmology. So cosmology is a sub-branch of astrophysics, and it deals with the study of the origin and the evolution and really the nature of the universe. So topics that you might have heard of that are included in cosmology are the Big Bang, inflation, the fact that the universe is expanding, how stars and galaxies have been formed in the first place, and then these two really mysterious partners, dark matter and dark energy. I'll give you a hint. Whenever you see dark in astronomy, it means we don't know what it is. So if you see dark something, that means it's just a unknown, really. And these are just kind of some topics that are included in cosmology, not everything, but they kind of give you a sense of what this field is really trying to get at. Okay. So this figure is probably one of the most referenced figures when it comes to kind of explaining the history of our universe and cosmology in general. And that's because it kind of like neatly sums up different things that have gone on in our universe. So the way that you kind of read this figure is that on the left, you have kind of the beginning of the universe, and on the right, you have up to current day. So if you were to, stand somewhere on this cone, it would be all the way to the left, or to the right, excuse me. And There's a ton to unpack here, of course, but I'll just kind of summarize really briefly so kind of the important events that we think happened in the history of the universe. So all the way on the left side, you have, the beginning. We call this, the Big Bang singularity or just the singularity. And we don't know what's going on in this period of the universe. It's very early on and very difficult to observe from our current day. But we think what was going on was that the universe was incredibly small, incredibly dense, and incredibly hot. And we think one of the first things that happened in the universe was this period of insane expansion that we call inflation. And it's really hard to kind of wrap your head around how crazy inflation was, because the universe expanded by a huge amount, by 78 orders of magnitude, by 10 to the 78 times. And just to try to put it into a comparison that even makes sense, it's like taking half of a DNA molecule and expanding it to 62 trillion miles. And this happened in a period of time much, much shorter than a second. So it was a really, really crazy time in the universe. And we think that's one of the first events that really happened. Now, coming out of inflation, we still have expansion, as you can kind of see on the figure. The cone is kind of getting bigger, but it's not getting bigger at such a high rate. And we think right after inflation happened that we got this kind of emission of the first light to exist in the galaxy. And this light, as it's shown on this figure, it is called the afterglow light pattern. It's also called the cosmic microwave background. And it's been a really important part of our understanding of cosmology because, as you can see, it represents a really, really early time in our universe. Shortly after this light pattern was emitted, we had a brief period that was dark, and then we had the first stars start to form. As soon as stars start to form, they start to kind of gravitationally interact, come together to form a group known as a galaxy, including our own Milky Way. And then these galaxies kind of went on to form bigger groups of galaxies called galaxy clusters. And we kind of get a lot of clustering and formation. And then we get all the way over to, what we have today, where we can see, our own galaxy, we can see other groups of galaxies, and we know that the universe is populated with just tons and tons of these beautiful galactic structures and that are made up of stars, and we get all those, beautiful astronomy pictures that I'm sure you've all seen. So that is kind of in a nutshell what we think happened, up in the early universe up to today. And it's pretty hard, even for me, someone who kind of studies this on a regular basis, to really get a sense of, not only the physical scale, but also the time scale of how all these things happen, because it happens over, billions of years. It's kind of hard to put it into perspective. So I found this really cool video that tries to give you a sense of, what happened when in cosmic time by taking the entire cosmic timeline and just compressing it into a single minute. So I'm going to show the video in just a second, and I'll kind of explain a little bit what's happening beforehand because it goes by really quick. Basically, you're going to start at the very, very beginning, and immediately we're going to see, structures starting to form, because that period of inflation lasts, for such a small amount of time. We'll almost immediately see stars and galaxies forming. It'll kind of pan us around the universe, and then we'll come to Earth, and we'll see kind of the different stages of Earth happening, and you'll see how fast it happens, in the video, representing that Earth and life as we know it has been around for a really short amount of time. So let's go ahead and watch that video now. Okay, here we go. Okay. Yeah, you can see how it got kind of chaotic there at the end, where, I mean, humans just showed up for like a flash of a second. So that kind of gives you a sense of just the timeline of everything that we're talking about. And so one kind of important thing to note is that how our universe, expands, how it evolves, what happens to the things inside of it, like stars and galaxies. It all depends on what the universe is made out of. And this pie chart kind of represents our idea of what the universe is made out of. So you can see that ordinary matter, which is basically the matter that we understand, I'm made out of ordinary matter, stars are, galaxies are, it really only makes up 5% of this total budget of the universe. And you can see that dark energy and dark matter, which are both, kind of unknown to us, make up a really large amount of the total budget of what's in the universe. Now, that just goes to show that, although we kind of have this cosmology cone, we have an idea of what's going on, there are a lot of open questions. And, I just highlighted some open questions here. There are many, many more. The first one is, did inflation really happen? That period of rapid expansion that I was talking about, did that actually happen or not? What was the universe like before there were any stars, when it was kind of the dark ages, as we call it? And of course, what is dark matter? How much of it is there? And the same question for dark energy. So in order to solve these really important questions in cosmology, we're going to have to come up with new and innovative ways of taking data, of interpreting things, and really trying to chip away at that huge slice of the pie that is unknown to us, so we can get some answers. And that's where studying galaxy motions comes into play. So before we kind of get into galaxy motions, I want you to kind of think about the fact that everything in the universe is moving, is in motion. So first of all, our universe is expanding. Galaxies move through space. Galaxies are containing stars, stars are orbiting around the center of the galaxy. Nothing in the universe is stationary by any means. And so there are certain things that kind of look stationary to us, but if you observe them carefully enough, you'll find that they also exhibit some kind of motion. So this GIF is actually showing the Orion constellation. See right here, you might be able to recognize the famous 3 belt stars. And what's happening is this is a kind of simulation of our predictions of how the stars in this constellation might move and shift around over a period of about 40,000 years. So even though these constellations, have kind of been the same throughout human history and they've been studied by many different cultures, they will kind of shift over time, given enough time they will shift. And, you could have stars moving around a lot. And it's not necessarily a given that these stars are always going to form the same patterns that we see today. And what I'm really interested to do for my research is to create a picture like this, but instead of using stars, using galaxies. We're able to make these kinds of predictions for stars because stars are just simply much closer to us. We are sitting, we're orbiting around our own star, the sun, and it's one of billions of stars in the Milky Way. And we're able to observe those stars in the Milky Way much more easily than we are to observe a whole nother galaxy in a different part of the universe. So what I really want to do is I want to make this kind of prediction for galaxies. And galaxies are really great tracers of how the universe has kind of evolved in general, because they formed very early on in the universe, and their kind of dynamics and evolution really good, show and demonstrate very well what was happening in the universe at that time. Okay, so it may kind of seem like a no-brainer to study the motions of galaxies, but this is actually a very relatively new field of cosmology. And I actually, just went to a big astronomy meeting in January, and I was presenting some of my work. And a lot of the other scientists there told me that they had never thought of doing these types of measurements before. And why is that? It's not because it's like this, incredibly innovative idea, but it's just because it just wasn't possible before because our technology wasn't good enough. So it's kind of like, like watching grass grow. Like, sure, we know it can be done in theory. You could like potentially watch the grass, the grass should be growing. But in practicality, it's not possible because it's just so slow that you're not going to see anything. And that's kind of what was happening with these galaxy motions. We know that these galaxies are moving a lot, but they're just so far away that it's really hard to see that motion. And I should mention that like the motion is so small because it's so far away. It's not because the motion is slow. In fact, galaxies move at like hundreds of miles per second. It's just really hard to observe since they're so far away. And I have a little exercise for everyone to just kind of demonstrate how minuscule these motions are. So I can't see you all, but hopefully you'll play along. So what you do is you take your pinky finger and you extend it out to arm's length, and you just kind of observe how much of your field of view that your pinky actually takes up, including kind of all around you. So your pinky at arm's length approximately takes up about 1 degree. But we don't actually measure galaxy motion in degrees because degree is too big of a unit. So what we actually measure them is in arc seconds. So to get from a degree to an arc second, you have to take your pinky and you have to divide it by almost 4,000. And then for each piece of that, you have to divide it by 10 to the 6, which is, 1 with 6 zeros behind it. So can you imagine, how tiny a piece of your field of view would be taken up by that amount of space? And that's the amount that a galaxy will move over an entire year. So as you can imagine, it is a very, very small amount, and it takes a really powerful telescope to be able to measure that amount of change. Yeah, so let's talk about the instrument that I've actually been using to study these motions, because it's a pretty impressive instrument because it has to be so accurate. So one of the primary sources of this galaxy motion data has been the European Space Agency's Gaia satellite. And it was launched in 2013 and has been taking data ever since in optical wavelengths. And what it does is it kind of continuously scans the sky over and over and records the positions of objects. And because you have these records of the positions of objects over a large amount of time, you can see if the object has moved over time. You have these snapshots, and if you can see the thing moving, you know that it's exhibited some kind of motion. And this GIF that we saw before, it was actually generated using Gaia data on stars in the Milky Way. And one thing to note about Gaia is that it's actually primarily intended to look at stars in the Milky Way and map them out. It actually wasn't totally intended to observe galaxy motions, which are the ones that I'm interested in. But what kind of happens is as Gaia is scanning the sky, the galaxies are in the background just kind of photobombing, the experiment. So not only do you end up with some really great stellar information, but you also end up with a lot of really cool galaxy information, which can be kind of used for cosmology. And Gaia just had part of a data release came out in December, and it turns out that they had recorded the motions of 1.5 million galaxies, which is a totally unprecedented, amazing, exciting amount of galaxies and different motions that we can look at. So the Gaia satellite is a really cool piece of technology, and I'm going to show about a 4-minute video explaining, how the telescope actually functions. And 2 things to kind of note before the video is that the video actually won't even mention galaxies at all, because like I said, Gaia's kind of primary mission is to study these stars in the Milky Way. But I ended up using its data to look at galaxies. And then the second thing is that they kind of mention the term CCD a lot when they're talking about the camera. And for practical purposes, you can just consider, CCDs to be mini cameras that kind of make up a bigger camera. So let's go ahead and watch this video about the inner workings of the Gaia mission.
With respect to us. One billion stars. This is the number that the European Space Agency mission Gaia will reach, mapping each star over 70 times to nail down their position, movement and characteristics. In the end, we will hold in our hands the most precise three-dimensional map of our galaxy. But how exactly will the mission measure such a vast number of stars? With its two telescopes, Gaia looks at two patches of the sky at the same time. A series of mirrors guides the light to the camera, the most powerful camera ever flown in space, with 106 CCDs and almost 1 billion pixels. When light from the first telescope reaches the camera, the first column of CCDs in the star mapper, on the right, selects the stars that will be followed and measured. When light from the second telescope reaches the camera, the second column of CCDs in the star mapper selects the stars that will be measured. As Gaia scans the sky, the light from both telescopes moves across the camera. But not all data need to be read out and stored. The onboard computer assigns a small patch or window around each star. As the image of the star moves across a row of CCDs in the camera, the star's position and brightness in this small patch on each CCD are recorded. This method is an optimization to deal with the enormous amount of data collected by Gaia's camera. Only a few dozen pixels on each CCD contain information about the star, so only those are read out and the corresponding data stored. The largest section on Gaia's camera is the astrometric field. As the image of a star moves across its 9 columns, each CCD measures the star's position and brightness. Then the starlight passes through 2 special prisms that direct different wavelengths to the 2 columns of CCDs in the photometer. This provides information about the star's temperature, size and chemical composition. Light from a subset of stars also reaches the radial velocity spectrometer, 12 CCDs that are used to measure how fast stars are moving with respect to us. For each star, the information collected by all CCDs is compressed into a data packet and stored in the computers on board Gaia. This process is repeated over and over for each star. An average of 2 million stars are measured every hour, generating a total of about 50 gigabytes of data every day. This is equivalent to more than 10 DVDs worth of information every day. The data packets for each star are transmitted to Earth, where they are received at the European Space Agency's ground stations. The data are processed and analyzed by astronomers, who use them to investigate the three-dimensional distribution and physical characteristics of stars. When all this is done, Gaia will have created the most precise three-dimensional map of our galaxy, the Milky Way.
Awesome. So that was a really neat video, kind of showing us the inner workings of Gaia and really the innovation that they did to make an instrument that could measure these motions, of the stars in the galaxy, and of course also of galaxies in the background so precisely. I should mention that there are a lot of challenges working with these galaxy motions because they're, it's kind of a new field, and there are a lot of things to consider when you look at the motion. So the first challenge with working with the galaxy motion is simply that the motions are really small. And this can kind of lead to large observational or systematic errors in the data. It also takes a long time to see any changes. Remember when we were talking about, our pinky and how the galaxy will move only a tiny, tiny fraction of our pinky over the course of a year. Sometimes that means you have to wait multiple years to do it. Another thing to think about is that galaxy motion signals are kind of complicated and overlapping. So there may be one effect that causes a galaxy motion, and then a totally different effect that causes the galaxy motion, and they're acting on the same galaxies. So their signals kind of become jumbled and overlapping, and it can be a little bit of a statistical chore to kind of separate out the signals and kind of extrapolate the physics underneath them. And then finally, like we've kind of talked about, the Gaia satellite is not optimized to observe galaxies, but it's kind of optimized to observe nearby stars. So that just means that you just have to be a little bit more clever about how you extract the data and how you interpret the data. That being said, there's a lot of really cool things that you can do with these galaxy motions. So let's get into that right now. One of the first awesome things that you can do with galaxy motions is that you can study the formation of structure in the universe. So what I mean by that is when we think about how the structures of our universe, meaning galaxies and stuff like that, formed, we think of it as forming in a hierarchical way, meaning that smaller things formed first. So we think that stars formed, and then stars kind of collected together to form galaxies. And then these galaxies clustered together to form galaxy clusters. And then these galaxy clusters form these gigantic structures that are known as large-scale structure. And I've put a little picture of a simulation of what large-scale structure looks like. And this is the largest form of structure in our universe, the largest construction of our universe, you can think of it as. And it kind of shows in this picture, just a huge web of these galaxies and galaxy clusters together. So, of course, this is of huge interest to cosmologists who want to know the nature and what was happening in the universe, because this structure formation is one of the best ways we can observe what's actually going on with our universe. And one of the really cool things about studying this structure is that people have made some really awesome simulation videos of kind of it all coming together. So we're going to watch yet another video in a little bit, and this video was generated by some simulations run on some supercomputers, and it kind of starts off showing us some hydrogen gas in the very beginning of the universe, and then the gas will start to form stars, and then at a certain point you'll see the colors change, and then it'll switch over to tracking stars, and then you'll see the stars kind of forming into clusters. And it's just a really beautiful simulation visualization. So let's go ahead and watch kind of our universe form structures from gas all the way to large scale structure. By the way, I did not choose that music. That was the music that they chose, the creators of the simulation. But yeah, I really love those videos because first of all, they're really beautiful, and second of all, they just they really show you like the complex dynamics that are going on in the universe, and just really how cool it is how things come together. And by the way, I should mention that really the primary force that's driving all of that motion and all of that commotion is just gravity. And it can form these beautiful structures that we see today. But as you saw, in that video, there's a ton of motion going on. When it transitions over to galaxies kind of swirling around each other, we know that there's a lot of galaxy motion, and that galaxy motion is, very much continuing today. We still have galaxies whizzing around each other, like you kind of saw at the end. And wouldn't it be great if we could actually observe that in real time? Remember that galaxies move at incredible speeds. They move at, 100 to 1,000 kilometers per second. That translates to, hundreds of miles per second. And if we can actually watch that happen in real time, then we can learn a lot about galaxy clusters. And one of the things about galaxy clusters is that we think that they're about 80% dark matter. So if we're able to actually watch them evolve and move around in real time, then we can get a really good sense of how much dark matter there is in that galaxy cluster. And really the only way we have of studying dark matter at the moment is to just see how it exerts gravity on other types of matter. So galaxy motions have a really big potential for letting us observe that really cool galaxy motion that will tell us a lot about dark matter. Another really cool thing that galaxy motion can tell us about are gravitational waves, and I'm sure you've heard about gravitational waves in over the recent years, because they've been kind of this really exciting new forefront of astronomy. And we're actually going to watch our last video that explains what are so cool about them. And I include a lot of videos because they're just amazing videos out there that people have done on YouTube that really nicely summarize them up with a lot of nice visuals. So let's watch one last video here.
Gravitational wave. It's a ripple in the fabric of space and time. Imagine that space is a giant sheet of rubber. Things that have mass cause that rubber sheet to bend, like a bowling ball on a trampoline. The more mass, the more that space gets bent and distorted by gravity. For example, the reason the Earth goes around the Sun is that the Sun is very massive, causing a big distortion of the space around it. If you just try to move in a straight line around such a big distortion, you will find yourself actually moving in a circle. That's how orbits work. There's not an actual force pulling the planets around, just a bending of the space. Gravitational waves are produced whenever masses accelerate, changing the distortion of space. Everything with mass and/or energy can make gravitational waves. If you and I started to dance around each other, we would also cause ripples in the fabric of space and time, but these would be extremely small, practically undetectable. Now, gravity is very weak in the scale of other forces in the universe, so you need something really, really massive moving very, very fast to make the big ripples that we can detect. How would you observe a ripple in space? If the space between you and me stretched or compressed, we wouldn't notice it if we had made marks on our metaphorical rubber sheet, for example, using equally spaced rocks, because these marks would also get stretched further apart. But there is one ruler that doesn't get stretched, one made using the speed of light. If the space between 2 points gets stretched, then light will take longer to go from one point to the other. And if the space gets squeezed, light takes less time to cross the 2 points. This is where the LIGO experiment comes in. It has 4-kilometer-long tunnels and uses lasers to measure the changes in the distance between the ends of the tunnels. When a gravitational wave comes through, it stretches space in one direction and squeezes space in the other direction. By measuring the interference of the lasers as they bounce between the different points, physicists can measure very precisely whether the space in between has stretched or compressed. And the precision needed is incredible. To detect a gravitational wave, you need to be able to tell when something changes in length by a few parts in 10 to the 23. It's like being able to tell that a stick 1 sextillion meters has shrunk by 5 millimeters. The effect of a gravitational wave is so minuscule and easily confused with random noise, you need a smart data analysis technique. Scientists hope to identify the patterns of gravitational waves by comparing the wiggles they measure in the experiment to the wiggles they expect from the gravitational waves. That's like trying to identify a song being hummed at a noisy party. A very, very noisy party. Imagine your whole life you had been deaf until one day your hearing was restored. You'd be able to explore the universe in this whole new way. That's why detecting gravitational waves is so significant. It's a completely new way of studying the universe. Anytime there's a new way to investigate the universe, we discover things we didn't expect. It's really about looking for new things we didn't know existed, examining the extreme edges of our knowledge of physics, and testing our theories about how the universe works.
Great. Yeah, that video does a good job of kind of explaining, physically, why are these gravitational waves happening? And, when the video mentions that these gravitational waves can be formed by, these two really massive objects orbiting each other. But another type of gravitational wave that can form are actually resultant from inflation. So it's not necessarily that there's two massive objects orbiting each other, but we expect there to be a kind of relic gravitational wave signal from very small fluctuations that were magnified during inflation. And this is really significant in the field of cosmology right now because it basically represents like the next forefront of cosmology. And whoever, is able to discover these primordial gravitational waves from inflation will certainly get the next Nobel Prize. So there are many, many types of astrophysical observatories that are kind of racing to be the first ones to detect these gravitational waves. And kind of to explain to you why they're so significant is if we look at our, cosmology code, the first time that light shows up in this picture is, at this kind of bluish, greenish pattern, the afterglow light that happens after inflation. And if you think about it, astronomy for the longest time has really just been studying the light from the universe. Our telescopes are basically giant buckets for light that comes from stars and galaxies. And it's what we've been using to observe everything. So how can we possibly observe the universe before light even really existed in the form that we know it today? It's like, sending someone into a dark room and asking them to describe what's in it. They're going to be like, I have no idea. There's like no light here. And that's kind of why, like, when we don't know when something is in astronomy, we call it dark, hence dark matter and dark energy. But imagine, sending that person into the same room and then suddenly they hear a dog barking. Then they're going to say, hey, there's a dog in here, and that's kind of what gravitational waves are able to do for us. They're able to open up like a whole new sense, in a way of speaking, to the field of astronomy. And a lot of times that's why you'll hear gravitational waves referred to as cosmic sound. Now, luckily enough, it turns out that we may actually be able to measure gravitational waves using galaxy motions. So what happens in this case is there's some distant galaxy and it emits some light. And as the light is traveling to us, it's kind of traveling over this kind of background noise of gravitational waves that are just, permeating out throughout the universe from inflation. You can kind of think of them as like the surface of the ocean. We know the surface of the ocean isn't flat. It kind of has these like patterns of waves that are just kind of going along. And so as the light is traveling to us from these distant galaxies, it kind of goes over these bumpy gravitational waves. And as we're observing it, it looks like the galaxy is wiggling back and forth. The galaxy isn't actually doing that, but it appears to be because the light is being distorted. So we can potentially look at patterns in galaxy motions and see this wiggling motion and say, hey, I know that was caused by a gravitational wave. And one of the really exciting parts about galaxy motions is that they have the potential to kind of target a really wide range of gravitational waves that can exist, and even a range that no other types of measurements can target right now. So this figure shows you the gravitational wave spectrum. It just kind of means like all the different types of gravitational waves that can exist at different frequencies. So the gray band will show you the different frequencies of gravitational waves that can exist. It's on a kind of a continuum. And at the top, we have the different causes of the gravitational waves. So the biggest one on the top says the Big Bang. That's kind of our gravitational waves from inflation. And then we also have some other sources like the supermassive black hole binary merger or the compact binary mergers. Those are kind of the things that the video was talking about, where there's two really massive objects circling each other. And if you look below the gray bar, there's different types of instruments that are either in existence or have been proposed that we could use to measure different parts of the gray bar. So all the way on the right is the terrestrial interferometer. Terrestrial just means it's on Earth. And that's facilities like LIGO, which of course won a Nobel Prize for detecting gravitational waves. And then on the other side, you have three more types of proposed observatories that, that are kind of in the stages of being built or are proposed being built. And you can see they also tackle different chunks of the gray bar. Galaxy motions are so new, I had to add my own little part to this figure. But, my group and other research groups theorize that these gravitational waves could measure a really wide amount of this frequency range of the gray bar, including the same things that the CMB polarization can measure, and also just the whole, its own whole chunk between CMB polarization and pulsar timing arrays that no other proposed thing can measure. So galaxy motions could prove to be a really important part in piecing together this entire picture on gravitational waves in the future. And I just wanted to show you kind of an example of a prediction that we've made. So I have on the left, it's just a map of wind patterns on the Earth. And you can see, the shape of the colors kind of show you the direction and shape of the wind, and the colors kind of show you where the wind is stronger versus weaker. And we've made that same kind of map for the whole sky for a type of galaxy motion that might be induced by gravitational waves. So if you look on the other panel, you can see this crazy swirling pattern, looks kind of psychedelic. Well, we postulate that maybe a gravitational wave pattern could look like that. So if we observed galaxies in the sky moving around in a pattern that matches this, we might be able to say, hey, that was caused by gravitational waves. And that can be potentially used to just measure the amount of gravitational waves present in the universe, or also potentially to confirm inflation and win that next Nobel Prize. That's kind of a stretch though. It's hard to win Nobel Prizes. Okay, so I've told you about kind of the basics of cosmology, galaxy motions and what we can do with them. And the future for galaxy motions, there are some things kind of coming down the line that are really exciting to look at. First of all, the Gaia satellite that we saw a lot of videos about, it's going to, it's released some new data on 1.5 million galaxies, and the data is being analyzed right now. So we'll get some potentially really exciting results from that pretty soon. And then another potential is that there's another telescope on the ground actually that they're contemplating doing kind of a whole new upgrade. It would be like the next generation very large array. And it's a radio telescope, and it can also take measurements of galaxy motions. And the next upgraded version of it could take even higher quality galaxy motion data with better precision. All right, so that's all I've got for you today. Thanks so much for listening, and I'll take any questions you have.
Oh, that was fantastic. I hear all the applause coming through from everybody right now. Rachel, that was so exciting and so fantastic. Thank you so much. I in particular, I appreciate your talk, because none of these topics that you talked about are easy to explain and to think about. And I think you just did a fantastic job summarizing a whole bunch of different topics, which are so cool and yet very difficult to actually even think about for astronomers, let alone to explain to non-experts who are not working in the field. So thank you for that. I'll open it up to questions. If anybody has any questions right now, feel free to put them in the Q&A, and we do have some already. So if it's okay with you, Rachel, we'll maybe go through some of the Q&A, and I see lots of people are saying, great job, very interesting, and yays in the chat. So thank you to everyone for that. Let's see, the first question came in kind of near the beginning of your talk when you were, I think, initially showing your, the cone sort of diagram of how the universe has evolved. And the question is, why are early cosmic microwaves / light still around?
Yeah, so we think basically, you know, like I was kind of saying, like that this light was emitted at like a very specific point in the early universe. And then that was the first light that was able to kind of propagate around and act like light that we think of today. And it's still around just because there hasn't really been anything to stop it. You know, like once the light is emitted, it just keeps going, just keeps traveling at the speed of light. And it was emitted at a, you know, kind of in all places in the universe at the same time, which is it's kind of a trippy thing to think about. But we think that the universe was very uniform at that time. So everything was kind of happening in the same way. So that light was kind of emitted in the same way all over in the universe. And since that time, it's just been out here ever since, pretty much.
Great. Yeah, thank you. And like I said, some of these concepts are so mind-bending, even to the people who actually study them. It's really difficult sometimes to think about them. As you know, you well know, we get a lot of these questions at open nights because people are really awesomely interested in all of this stuff. Let's see, the next question is there a theory that there will be a contraction period in the future? And I think this is referencing to the fact that you talked about the expansion of the universe.
Yeah. So there's all types of like really interesting kind of geometry studies that go on cosmology, and geometry just kind of means like the way that the universe expands, you know, kind of like the shape of the universe, which is honestly a really confusing subject even for me, but it's kind of like down to like kind of the math minutia of how things work. But there are, you know, theories that, you know, theorize like a big crunch, you know, kind of like the Big Bang where the universe will contract. It doesn't seem like, you know, I guess fortunately, it doesn't seem like the observations really support those theories. Mathematically, they're totally possible, but it just hasn't lined up with the different observations that we've been taking of both the early and the like, you know, later universe. So I guess we'll see, but it might not contract.
Great. Well, we have some tough questions, by the way, I should say. The next question has to do with antimatter. And I believe the question is antimatter a possible candidate for dark matter?
Yeah. So the crazy thing about dark matter is that the only thing we really think that we know about it is that it exerts some kind of gravity. We don't know anything else about it. We don't know, you know, is it made up of like protons and neutrons, like normal matter? We have no idea. Is it particle based? Could it be something more crazy? So is there an antimatter theory for dark matter? Yes, only because there's like a million theories for dark matter. Yeah. But generally speaking, antimatter is different from dark matter. It's much more understood, and we don't think it can account for all the things that we think that dark matter does.
Mm-hmm. Great. Let's see, this might be a quick question. Is the Milky Way moving as fast as the other galaxies? I think this is when you talked about the typical speeds of galaxies. So is the Milky Way different, or is it kind of normal?
Yeah, that's a good question. I think I'm not totally sure what the certainty is on how fast our galaxy is moving, but it is a part of a larger galaxy cluster. I think it's our galaxy cluster is called like the Virgo. I think it might actually be a supercluster, which is, you know, a bigger cluster. And we are not this very center of that cluster, which means that there's, you know, we're attracted to the other mass that is around. So our galaxy is definitely moving, but I'm not sure exactly what speed it's moving at.
Okay, great. Let's see. There was a question, I think, that came in when you were talking about the formation of things in the universe, which I think is just more of a comment that says, you mean stars make galaxies and galaxies make galaxy clusters. And I think that is true, what you were trying to say. And then the next question along those lines is so there's no magic pole in the sun. It's just because it's heavy, like a trampoline, but with something really heavy. And I think that also refers to the video that you showed. I don't know if you want to say anything else about those, but.
Yeah, the video kind of like, it has a line that says like, oh, like there's no like force, it's just like this kind of shape. I semi disagree with that kind of comment because it, we think of the bending of space to be like the force of gravity. So, if you think of it as a bending, then you can kind of think of it that way, but you can also think of it, very successfully as an actual force of gravity, which we have a really nice equation for. So it's just kind of a little bit of a different perspective, but they kind of are the same thing.
Mm-hmm. Right, yeah. Let's see, the next question is, in your opinion, is inflation a reasonable theory or a plug that currently happens to fit the equations?
Yeah. Let's see. In my opinion, yeah, so inflation is like motivated by there's kind of like this like well-known like problem in cosmology where we see a lot of relationships between different parts of the sky that are separated by a really large amount. So, we kind of see the same bulk behavior over here in the sky versus over here in the sky. So inflation is kind of saying like, oh, they must have been really close together early in the universe, and that's why they exhibit the same behavior. And inflation solves that because inflation takes things that are really close together and expands them enough to the point that we need them to be today. So in that way, inflation can kind of be seen as like, just a plug to fit the math. And I think that, while we don't have solid evidence for it, it can certainly, that's kind of its biggest weakness. But again, like the primordial gravitational waves, like those will be like the best way to know if inflation is real or not, because that is going to give us like a real concrete signal that could have actually come from that period.
Yeah, and I have to just put in my own plug here. I think this is one of the reasons why this is so exciting, because you can really have an opportunity to actually possibly answer one of the biggest unknown questions that has been such a mystery for so long. Yeah. Wow, we've got a lot of great questions. So keep them coming if people have more. The next one is, will galaxy motion help determine if we are in a multiverse?
Oh, probably not. Like in kind of the multiverse theory, like kind of inherently says that like this universe is over here and this one is over here and they're not connected, So it's hard to think about how we could prove there's a multiverse when it's like inherently this is encapsulated and totally separate from like this other thing, So I don't think so.
Yeah. Let's see, the next question is there any prediction of what this will look like a few more billion years from now? Is the ever more expanding or more and more attracting each other via gravity? So again, like what are we kind of thinking? Where are we? Are we expanding, or are we going to be in a big crunch? Or, what's your thought on the latest information that we know about that?
Yeah. So it's interesting because we hear, the universe is expanding, but then we also hear like, these things are collapsing and, structures are forming from gravity. So what's happening is it's kind of happening at the same time. So the bulk universe is expanding, and we can see that like, the evidence that we have for a universe expanding is that we see like far away galaxies are moving further and further away from us. So that's still happening, but within like galaxy clusters and groups and whatnot, there's still contraction happening. So it's kind of like these smaller subsections of the universe are contracting due to gravity, but gravity can only work on such a scale such that the larger universe itself is still expanding. So we expect the expansion to continue, and we also expect gravity to continue. So we'll still get structure forming, but our universe as a whole will kind of be expanding. They're kind of like effects that happen on different scales depending on the size that you're looking at in the universe.
Mm-hmm. Let's see, we have another question that was also put in the chat and in the questions, which is a good one. What are the coordinates and origin in the universe that you use to measure motion?
Yeah. So that's one of the tricky parts actually about measuring these galaxy motions, is that what we've tried to do is we've tried to find galaxies that are really far away that we can't even perceive them to be moving. But when you use a strong enough telescope then that can detect so many like minuscule motions, like your anchor points are going to start moving too. So Gaia has like a couple reference quasars that are supposed to be used to calibrate the rest of the motions of the different galaxies. But unfortunately, those are moving too. So the Gaia team works really hard to try to, take out that effect of, your kind of ruler like moving around. But it does introduce a little bit of a systematic error into the data, which isn't so much a problem for stars, but can be kind of a big problem for galaxies. So it's a kind of a continuing struggle to get like a good anchor point for measuring these motions.
Mm-hmm. Yeah, definitely. Let's see, the next question is, do you measure the Doppler effect when measuring the motions of galaxies?
Yeah, so that's one of the things that people measure when they look at galaxies. You can look at, you can do exactly that. You can measure the Doppler effect and the kind of the redshift of their lines, and that'll tell you a lot about, how they're moving radially away from you. So either, directly towards or away from you. It's harder to use that information to tell how they're moving kind of across your field of view, but you can get a really good sense of how they're moving directly away or towards you.
Mm-hmm. Yeah, great. Let's see, we just have one more. So if anybody has any other questions, go ahead and put them in the Q&A and we can answer them if we can. The last question is a little bit of a different topic here, which has to do with string theory. And wondering if you're able to say anything about string theory and how it might be related to the topics that you discussed tonight.
I am not able to say anything meaningful about string theory. I think in relation to, this talk, it's like, this talk is dealing with like, the smallest unit that I'm kind of studying is like an entire galaxy. And string theory is very concerned in like, subatomic, very small scales. So I don't know anything about it.
Yeah, and I'll back that up too. I think string theory, there might be people kind of working on how string theory connects with gravity, as we don't necessarily really understand gravity itself very well. And there's these quantum theories of gravity and things like that. But I agree, it's kind of a completely different scale than the things you're talking about, which are the largest scales in the universe. String theory is almost the opposite end of that, the tiniest scales in the universe.
Right.
Yeah. All right. I think that might be all of the questions that I see in the Q&A. So last call, if anybody has any questions, go ahead and pop them in the chat or in the Q&A. And while we wait to see if there's any other questions, I just want to say thank you so much, Rachel. This was such a fun and exciting topic and talk. And, I think it was so great to hear everything that you're working on, and you do such a great job explaining it too, because by no means is any of this sort of easy to explain to folks. And so I really, really appreciate all the time that you put. Oh, and we have another question actually from Georgia, who's wondering if the VLA in its current configuration works for measuring galaxy motions, or does it need the upgrade in order to be able to do that?
Yeah, so the VLA, it has been measuring galaxy motions for longer than Gaia has been measuring it. The big difference between the VLA and Gaia is that the VLA is really good at focusing on just a small handful of sources over like a long period of time. Whereas Gaia scans like the entire sky. So Gaia gives you, a much bigger picture than the VLA does. And the reason why that's really helpful for studying galaxy motions is because when we're doing cosmology, we're really interested in the patterns that are manifesting across the entire sky. Because if they're across the entire sky, that means that they're related to, the entire universe, if they're happening in all places. So yeah, VLA does work right now for doing galaxy motions, but unfortunately it's hard to do cosmology specifically with just the small amount of sources, relatively speaking, to the Gaia data. And that will kind of continue to be true with the next generation VLA as well, but we'll just get like much smaller error bars on our data. So we'll have like, kind of higher quality data out of the VLA, which we might be able to do something with.
Mm-hmm. Actually, I have a question. Do you happen to know how much longer is the Gaia mission? How many more data releases should we expect? Do you think you're going to be able to constrain your predictions much better in the next couple of years? You know, if there's more data releases coming?
Yeah, so they are currently on their last like planned data release. So they did kind of like a two-phase approach. They released something in December, and then they're going to release something else. I think very soon, or they just did. But this year they're going to release another, the last part of it this year, and that's like it kind of its last of its like planned mission timeline. Of course, like as long as it's continuing to function, they're of course going to use it. They're not just going to abandon a perfectly functional telescope. But one of the biggest challenges to the Gaia data right now is actually just that there are so many systematic errors in the galaxy information. So like I was kind of mentioning, like Gaia is really optimized for the stars in the Milky Way. Mm-hmm. So there's all these like patterns that shouldn't be there in the galaxy motion. That's just due to some kind of, you know, maybe miscalibration or miscalculation with the systematics, but we're not quite sure what that is. So probably the best improvement that can come out of Gaia in the next few years is really just figuring out like what those systematics are and just removing that noise from the data.
Mm-hmm. Mm-hmm. Great, cool. We actually have another question, which is a great question, which is, what does a typical day look like for you with your research? What is it like to be a grad student?
Yeah, so I do kind of like the theory side of things. So, you know, when you're like a kid and you imagine that like physicists just like spend all day just like scribbling like on a chalkboard and like writing down equations and stuff. Like I actually do like a decent amount of that, which is not typical, I would say, for like what my other like peers in grad school do. So I do a lot of like kind of math involving like geometry about like, you know, kind of like how different length scales in the universe are kind of evolving over time. And my work is like completely done on the computer. So I don't use like a lab or anything like that. And I basically just kind of like think about my research and then look up things and then, you know, get on my programming software and like try some things, look at some graphs, all very exciting stuff. But yeah, that's kind of like how my research kind of goes. It's just like, because I'm on the theory side of things, it's a lot of just like thinking and trying out some things and seeing if those predictions make any sense.
Mm-hmm. Awesome. Let's see, I think that might be all of our questions, and we're a bit past the hour. So I'll just say one note that we did record tonight. So if you came in late or you missed something and you'd like to watch it again, we will be posting this video on our YouTube channel tomorrow or the next day or so. So if you want to watch it again or share it with your friends, please do so. And I think with that, yeah, I don't see any other questions. I do see some thank yous coming in. And I would just like to add my own really heartfelt thank you. I really, really appreciate this. Your work is so awesome and so exciting. And I appreciate you sharing it with all of us tonight. And hopefully we can have you back to Nantucket for a visit sometime in the future once travel is possible again. And, you know, in the meantime, take care, and thank you all for coming tonight, and we look forward to seeing you in our summer speaker series, which we'll announce in a month or so.
Yeah, and thank you, Regina. Yeah, I just want to do a shout out to you and also to my research mentor at MMO, Lindsay King. Yeah, being an intern at Mariah Mitchell was amazing. It was like one of the best summers of my life, and it's like 100% the reason why I'm like here in grad school and everything. So yeah, I'm super happy.
Yay. Well, we loved having you, and I can't wait to have you back. So yeah, awesome. All right. Thank you again, and thanks everybody for attending, and have a good night.